energy spectrum measurements. This is causing me a lot of confusion. So I'm going to try to give a little bit of background on why I confuse myself on this, why I won't accept some of the explanations folks give for um, energy, energy itself. The challenge here is when you get into particle physics, into the core of the nucleus, into the core of the sun. The sun is almost pure energy equations to us. We see sunlight. Sunlight, visible light, is photons of energy caused by electron movement. So, that's what a photon is. If you go look at the definition of a photon, it is a quantum. Its very definition states it is a quantum, which is a sum that we can qualify, we can talk something about. As an individual particle, it gets very hard. Quantum mechanics is down there. But as a sum, we can look at the sunlight and get warm. That is the sum of the energy transferred to us, is that heat that you feel. That is not electron movement. It is photons, quantum sums of the energy available to electrons. It is a discrete energy. It has no mass. It is what caused huge changes in physics equations, because that energy quantum is tied to electrons, is related to electrons. That is how we see that that energy was available to an electron, yet it is discrete energy. Now, the reason I keep this stance, this opinion, this position, is my background is in how we measure. It is, if you trace out National Institute of Standards rules, sciences on how a multimeter works, how an oscilloscope works, how a photomultiplier tube works, how a crystal scintillation detector works, how thermocouples work. My training, education, and experience was in that level of instrumentation. My career actually moved up from that level of measurements into the use of that data, hard data, with many decimal places of concern. And back in the day, we worried about the accuracy of floating point precision on the computers we gave the numbers to. That's not a consideration very much today. In general desktop computing, do you worry how accurate your floating point processor is? Do you test it? Do you have a need to test it? Do you have the tools to test it? So you can go round and round with this. But here is a fact. Photon is energy. It has no mass. It's one of the few particles we talk about and describe that has no mass. With no mass, energy equations don't work, because m, mass, is a part of those equations. I've talked before about boundary layer physics, where the rules actually change. So one of those boundaries is subatomic particles. We have seen a light. We have seen movement of electrons and what it can do. We know they're very related. We know that the equations tie them in together. But you can go back. These particles exist, right? Let's go to nuclear, subatomic particles. The alpha and the beta and the gamma energies. Each one of these is a discrete type of energy measurement that we have learned how to perform. These are all quantum information packets, though, which there's that word again, that word applied in a very specific meaning, kind of like putting evolution out there. When A. P. Z. Myers says the word evolution, it has a very specific meaning and context to what he's talking to. And he has to keep that, or else people can play with the conversation and make it into something else. So, discrete energy measurements from a measurements perspective keeps me from blending these things together. There is a reason to, there is a need to. When you're considering energy equations, when you're doing pressure differentials, PV equals T, you never consider the energy of alpha, beta, and gamma particles, mostly gamma that we're talking about at this point, because whatever you're working in has shielded the alpha and the beta out, right? So they're high energy, low penetration particles because of their interferometry properties, how they interact with other particles. And gamma particles basically don't do that. But I spoke to, these are energies we're measuring. Nowhere in that PV equals nRT equation is gamma energies considered, even in a closed system. Yet we know the gamma energy is there. It is so statistically insignificant as to not be worried about, right? It just does not matter for most people doing physics. Anybody in the engineering field without specific need to go there wouldn't. So Sean Carroll has some amazing presentations, simply amazing. And I wish he would help solve out this question about the discrete nature of these particles we're talking about and how important or unimportant they are. I feel they're important. You have to know energy density in order to talk about safety. There is some point where that energy density becomes a high risk. It will kill you, whether it is RF energy, radio waves, in higher frequencies because of how energy is transmitted and carried. This is much like our nation's energy policy, only that's the raw energy it takes. Each one of us consumes, I think it's 2 kilowatts a day. I don't remember the number. Go look at it. Call me on that one. In order to get that energy delivered to your body, how does that work? These are conversations that are had. So, pieces out, more pieces. And, yeah, boomers.